I'll begin with a word of prayer. Dearly Father, we thank you for this day. Thank you for the students. Just ask you just help us today. Just bless our work, Lord. In your name I pray. Amen. So as I was just telling you guys, this is Sam had a question about some of the details of this example, which problem 29 is based on. I'm not saying you have to literally follow this example to do problem 29. You can do something like this example. I want you to try to understand for problem 29 why it is that when why partial f partial z is equal to df dz in the context of a gamma differentiable function, and why partial f partial z bar is 0 for a dual number differentiable function. Those are some things we should uncover in a solution to problem 29. But these are actually, if you follow my definition of 6.33, these are the algebra derivative and the conjugate derivative with respect to the dual numbers. Again, I have to change coordinates from the standard xy coordinates to y1, y2 coordinates because unfortunately E2 is a zero divisor for the dual numbers because epsilon squared is 0. So I can't just straight away do it. I have to come up with a new system of coordinates which is with respect to an invertible basis for my conjugate calculus stuff to work. All right, enough about that. That is of lesser importance to what else I'm talking about today, so put that away. So getting back to our story from last time, I want to talk about invertibility. Local invertibility. So you guys know, let's just go back to calculus 1 for a second, right? What's a local inverse? If you got a function, right? And if this is its graph, right? Y equals f of x. What does it mean to find a local inverse for f? So what you want to do is you want to pick some kind of subset of the domain, maybe like this, on which if you look at the graph over that, right? If you look at the graph over that set, let's say U, then you can see that f restricted to U, right, which is a mapping from U to the reals. How's it defined? F restricted to U of x is just equal to f of x for all x in this subset U. Now, what condition do you need? What condition do you need on this set U in order that this restricted function have an inverse, that it be invertible? Yeah, you need that it's bijection. I don't think this has to be on to R. 1-to-1, right? So it's sort of a graphical way of thinking about it is the graph has to pass the horizontal line test with respect to at least, the red part. It doesn't matter if the function hits these values other places. As long as it just hits one value for that restriction, then it's going to be 1-to-1, right? So, pass the horizontal line test with respect to the restriction. And so you can talk about local invertibility. Local invertibility would just be that there exists some U, right? There exists some U such that if you pick a point, right? So if I pick this point right here, the question is the function locally invertible there? Well, it's going to be troubling if I get past the top of the hill here, isn't it? So with respect to this point P, yeah, I should probably choose something more like this for the U, right? But if you look at it, it would still pass the horizontal line test there, right? Where is this function not locally invertible? On my picture, there's 2 points that it's not locally invertible. The top of this hill right here, and the bottom of that hill right there. That's the place where we could not invert the function because it doesn't matter how small you shrink an open, at least not with respect to an open set around that point, because you'll necessarily hit, 2 outputs. And take a horizontal line, put it through the graph, you're going to hit 2 outputs, right? Which is going to mean that you can't find a local inverse for that restriction. What's special about those 2 points is that those are the places where the derivative is 0, right? So in short, there's a local inverse. There's a theorem if we have a function of one variable in calculus 1, if it has a non-zero derivative, right, and that derivative is continuous, then certainly there exists a local inverse near that point, right? We can restrict the domain small enough that we can find an inverse function, right? And that's basically just calculus with graphing, and you know the fact that we have to pass the horizontal line test to find an inverse, right? It's really nice that essentially the same theorem is true for complex functions. This is the theorem. If we have a function, say from the domain, which is some subset of the complex numbers, to the complex numbers again, and there exists z naught in the domain such that f is, you know, complex differential, is holomorphic at z naught, that's what I want to say. What's that mean? That means that its complex derivative exists at z naught, and at least on some open set near z naught, right? So it's complex differentiable in some neighborhood of the point z naught. If we have all that, and a little bit of, in this condition, f prime of z naught is not equal to 0, then there exists a local inverse to f near z naught, right? Which means that, what that means is that you can find, so here's a picture of what's going on. Here's the domain of f. Here's the point z naught. So to find a local inverse means that I can find some open set around around z naught, all right? And we can just take it to be a disk for the sake of discussion here. Some open set u, right? Such that if we look at f restricted to u, and we let that go over here to, say, f of u. See, Jonathan, we'll get your bijection now. So I just made the range for this restriction. I mean, if we make the range the image of the restriction for the domain of the restriction, it's automatically that would automatically be a surjection if I take this mapping to go from, say, u. But technically speaking, this is not actually the restriction, though, so I should put I don't know, tilde or something. There you go. Is that a bijection is a mapping which is both one-to-one and onto. Okay. So I put a tilde over it because, to be fussy, the restriction doesn't change the codomain. See, like if f is a function from the reals to the reals, then by definition, common definition, the restriction of f just gives a new domain. It doesn't mess with the codomain. If I want a bijection, I also need to mess with the codomain. I need to make it smaller so that I actually have a bijection. So if you call this f of u, we could call it v for the sake of discussion. Then there's also an inverse function. So let me just give this thing a name. Let's call it g. Then there's also a g inverse down here. And that's what it means to have a local inverse, is that you can restrict it down such that you get a one-to-one mapping, which can be inverted, and then that also has an inverse from v. And also, more than that, we get that the inverse is also holomorphic on v. All right? So that's the inverse function theorem here. Let me just talk about the proof a little bit, not too much. But the proof is essentially this. If f is holomorphic at z naught, then f prime of z exists near z naught, and the Jacobian of f is what? Well, the Jacobian matrix of f is ux, vx, uy, vy, but that's equal to what by the Cauchy-Riemann equations? It's ux, minus uy, right? Oh, fine. I'll put the minus up there, and what do you want? What do you want from here? let's put Vx. We'll keep the Vx down here. Put a minus Vx up there, yeah? So sorry. Now what's the determinant? What's the determinant of the Jacobian? For this complex differentiable function. Check it out. It's ux quantity squared plus Vx quantity squared. But what is that? You might recognize that as the modulus of ux plus ix, ux plus vx, ivx squared, which you might recognize, since we're talking about a complex differentiable function, as f prime of z modulus squared. But there you go. See, because that means that if we have, so thus, the determinant of the Jacobian of f at z naught, right, is equal to the modulus of f prime of z naught squared, which is not equal to 0. So this shows that the determinant, it shows that the Jacobian matrix is invertible at the point z naught, all right? And the other data that I have implies that this function is continuously differentiable at the point. So then we refer to a theorem of advanced calculus called the inverse function theorem, which says that if the Jacobian's invertible and the function's continuously differentiable at the point, then there exists a local inverse near the point. All right? And then advanced calculus says that the inverse, the derivative of that inverse function is given by the inverse Jacobian, which then when you sort through it means that because the inverse matrix of a regular representation is again a regular representation of the complex numbers, it will follow then that the inverse matrix is also a matrix which represents the Cauchy-Riemann equations holding for the inverse function. So those details are more clearly spelled out in the notes with about a third a page of calculations. They're not. But you know, this isn't one of those proofs that I actually want you to know for the test, because really this is just like putting wallpaper over an advanced calculus proof, right? I mean, it's not really a complex thing we're doing here. We're just referring to a theorem of real analysis. There is a native complex proof you could give here. What you would do is you would use the fact that the complex derivative is non-zero. You could build a linearization to the function near the point, and then you could build a sequence of functions which converges to a local inverse using that linearization and its iterates. But that, again, would be just reproving the inverse function theorem for real analysis in this context. So anyway, I'm really less interested in the proof of this theorem than us using it. So let's use it, if that's okay with you guys. So what's the principal application of this? How about this? If we look at f of z equals to e to the z for f going from, what's the domain? Complexes, right? What's the range? Well, we'll let the codomain be c. If I say that, is this function a surjection? Is it an onto map? Does the complex exponential hit everything in the complex plane? I see one yes, I see one no. You're both about like 99.9999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999 So it's nearly a surjection, but not quite. Now, is this an injection? Like if I have f of z1 equal to f of z2, what can you tell me about z1 and z2? That means that z1 is equal to z2 plus what? 2 pi I z. Well, excuse me. It's an element of, to be more clear. Yeah. In other words, you could have arguments differ by any 2 pi multiple of I, any integer multiple of 2 pi I, because of the fact that there's a sine and cosine in there, right? Remember, what does e to the z look like? If you forgot, this is it, right? So the point is, if we look at y, and if we look at y plus 2 pi k, for k in the integers, then both of those output the same sine and cosine, and so give us the same exponential, right? The exponential is not 1-to-1, right? But can we find a local inverse for the exponential? Can we do that? Can we do that, right? Can we set w equals to e to the z, and can we solve for z? Can we solve that for z as a function of w? Right? Well, we can do that, but I mean, can I solve for z? I mean, we've talked about this before. What did we use? What's that? Branch cuts? Yeah. I mean, so we have many choices is the point. Yeah. We could use the principal logarithm. That would be one choice, but there are others, right? The logs of alpha. So let's see here. So that one question, but I was trying to apply this theorem. So how does the theorem get applied? How about this? F prime of z is what? d dz of e to the z? Yeah? The derivative of e to the z is, as we proved before, e to the z, as we were just discussing, everywhere non-zero, right? So that means that the exponential, you can find a local inverse for with respect to any point, right? And we've studied this problem in more depth before. We know we can actually find an inverse with respect to a restriction of the complex plane such that the horizontal strip doesn't have y extend past a 2 pi z, like past a 2 pi strip, right? So to draw a picture of it, the principal logarithm is actually the local inverse with respect to this u, right? If we take f restricted to u inverse of w, it's equal to the principal log of w. This is pi, and I mean here y equals pi, y equals minus pi. Yeah. And let's see here. Where does that map to? What would if I looked at, I guess I could ask the question, if this is my u and not including the strips, what's the log of u? What's that actually? What set is that? Let's think through it. Yeah? So I'm asking, well, let me put down some more formula. What was the principal logarithm? It was, let me get into a little bit more detail here, yeah? So the principal log of w would be the natural log of the absolute value of w plus I times the argument of w. And I see I'm sorry guys, let me fix something here. I think this is going to be a more productive discussion if I use these here. And admittedly, I'm falling into the same thing I criticize pre-calculus professors for, the need to write the function, the inverse function, in terms of the same variable as the function, which in some sense is bad form because you kind of like to distinguish z and w. Yeah, but okay, fine. So using z for the variable of the inverse function because it's more familiar to us in our visualization. We have y is pi, y is minus pi, and so what is this output as we think about inputs from u? How about the real part? How big can the real part get? Yeah, I'm not. Wait a minute. I think I've talked myself into a. Let me. You know what? Let me just take a breath here, draw a picture. So here's the idea. I want to think about restricting the exponential to the strip, right? And so I'm saying the log should be the inverse function. I guess the question I'm actually asking is, what is the... Okay, here's the question I should be asking. What's the range of the exponential if we just feed it things from the strip? That's actually what I'm interested in. So sorry, I am getting... all right. What does the exponential map to if we feed it this horizontal strip that goes from pi to minus pi for y? So I think I've worked through this before in like a video or something, but just to review briefly, if this is z, right, if z is equal to x plus iy, then over here, an image, over here, w equals e to the z, what's it look like? E to the x, e to the iy, right? So what can you say about the x? I mean, x is ranging over the strip. It goes to minus infinity that way. It goes to infinity that way. So the e to the x term does what? It gets as big as you want, and it approaches 0. It doesn't hit 0, but it approaches 0. So basically, this could be anything except 0, right? So it's, and by anything, I mean anything in, let's just get to the point. This is anything in 0 to infinity, yeah? Okay. And how about e to the iy? Well, that determines the direction of the output, right? And so we're saying that the input's going from minus pi to pi, which means it's sweeping all the way around. It's just not hitting this axis, this piece over here, right? So basically the image, so I'm trying to say, is that the range of the exponential restricted to the strip, which I'm calling u for the purpose of this discussion, is just it's the slit complex plane, right? And the range of the restriction is the domain of the local inverse, which we call the principal logarithm. Right. Now, to be fussy, I did define the principal logarithm on the complex plane with that ray included as well. But if you don't mind, I'm not going to fuss about that. Do you want me to? I mean, fine. If you want me to be really picky, it's the log restricted. Fine, you got me. Technically speaking, it's that. All right, great. I was anticipating Sam's eventual comment, but anyway, my point is that the principal logarithm is a local inverse for the exponential. Is all I'm saying. And you could say the same about log sub alpha. It's just going to be the local inverse for the exponential with respect to other horizontal strips. All right. So the larger point here is that you could figure out the derivative of the logarithm using calculus 1. I would like to point that out to you. That still makes sense. So, you know, if we say that, you know, w equals log of z, right? Then that implies that e to the w is equal to z. And then we can and also that, and by the way, w is function of z, right? So if you look at all the theorems we have here, we can do implicit differentiation. So I'm taking the exponential of both sides, yeah? And then if I differentiate this equation with respect to z, what do I get? I get e to the w dw dz by the chain rule, plus, listen to me, equals to 1. So therefore, dw dz is equal to 1 over e to the w. What is e to the w equal to, though? Oh, it's z. So there you go. The derivative of the derivative of the logarithm, principal logarithm, is equal to 1 over z. I gave you a rather different proof of this the other day, didn't I? How did I prove it last time? We found the component functions for the logarithm. We showed that they're continuously differentiable. We checked the Cauchy-Riemann equations, and out popped this formula. But we could also calculate it calculus 1 style. And you can do the same thing for the log sub alpha, right? Because log sub alpha also has exponential as its inverse function. Okay, technically the exponential restricted to the what? The domain of log sub alpha. Excuse me, that's not right. Anyway, let me stop belaboring these points. Yeah. Okay, so yet another way to look at complex differentiation. If the complex derivative is non-zero, it's a locally invertible function. So very nice. With that, we move on to something that I think is a topic that you're really going to enjoy. I enjoy it. It's very algebraic and also geometric. And it's just got all kinds of really, really neat aspects to it. One of the things that this conversation is going to require, though, is the introduction of what's called the extended complex plane. So let's just get that out of the way at the start. Extended complex plane. What's the extended complex plane? So we take C and, oh goodness, what was my symbol for this stupid? Do you guys, have you read enough of my notes to remember what my symbol is for it? C star? Okay, that seems right. C star is C unioned infinity. So what we do is we tack on an additional point to the complex plane, which we think of as infinity. And so you can do things like talk about neighborhoods of infinity, like the neighborhood of infinity. If I talk about a disk of radius epsilon at infinity, what that's going to be is z in the complex plane, such that 1 over z, the modulus of 1 over z, is less than epsilon. So something like that. No, I think that's it. But anyway, I should talk more about this in like a homework or something. But the bottom line is you can throw in infinity and you can talk about limits at infinity as well. Like this, for example, here's one limit. What do we mean by limit as z goes to infinity of f of z? How's that defined, actually? You define that to be the limit as z goes to 0 of f of 1 over z. So you make, basically you can do things with infinity by replacing functions of z with functions of 1 over z, and you kind of just make the natural catalog shifting from 0. 1 over 0, you think of 1 over 0 as infinity, essentially. Anyway, I'm not going to say more about that today. We'll come back to this some other time when it's more appropriate. All right? It's going to come up as we talk about the Mobius transformations that I'm about to talk about. So here it is. Definition. A Mobius. There's a couple O's over There you go. What's that called? A what? What he said? A what? Ah. Is it an umlaut? I don't know. With the two dots. Double dot. Double dot. That's definitely wrong. But Mobius transformation. What's that? Sometimes known as, AKA, fractional linear transformation. I kind of like that one more. Fractional linear transformation. I will often call them that. Some of the older books call them bilinear transformations. That I dislike immensely. Is any function of the form w equals to f of z. So here it is. It's az plus b over cz plus d, where a, b, c, and d are complex numbers. And what's the condition that we want on a and b and c and d? We want that AD is not equal to BC. Now, why do we want that? You guys have a homework problem. You worked it, and you figured out that the derivative, right? The derivative would be what? It would be that condition will make the derivative non-zero, right? At the points in its domain. It does. Exactly. So if AD is equal to BC, we have proved that. If AD is equal to BC, then this is a constant transformation, right? But if AD is not equal to BC, then this is a non-constant transformation, which, by the way, means the derivative is non-zero and it has a local inverse. Woohoo. In fact, these have global inverses. Yeah.
Can you show, like, directly without that theorem, what we get if AD is equal to BC? Like, what constant the function is equal to?
Let's see here. If what happens if AD is equal to BC? If AD equals to BC, then we'd have f of z is equal to az plus b over cz plus d. And I suppose if we multiply by d over d, something should happen, yeah? I don't know. What does that give me? ad z plus bd over cd z plus d squared. What did we say? AC was equal to, AD was equal to BC. I don't know. Yeah? I'm open to suggestions. So you said A is equal to BC over D? All right. Now, admittedly, then we need a separate argument for when D is 0. So that would be BC over D times Z plus B over C, Z plus D. Multiply this by D over D. BCZ plus BD over DCZ plus DD.
Oh, so it's B over D. Because you take D factor of B from the top and D from the bottom.
Say again?
Factor of B from the top because C equals D, assuming factor of D from the
Oh,
bottom.
okay. Cool. I didn't see it right off, but I see what you're saying. So we got B over D times CZ plus what was it? D and CZ plus D.
And then if D is 0, then you can get smaller.
Yeah. Now, And so, well, yeah. So there you go. What is it? Oh, okay.
I actually added something to the lecture that was pretty nice.
Oh. No, it's good. I appreciate that. But we have just managed to spend 5 minutes on the one case for this that does not matter. Sorry. But it's not. That's not your fault. That's Sam's fault. Actually, it's my fault for not like saying, no, I'm not going to talk about that. We don't care about that. That's the condition I'm putting on the thing. Ah. What's that?
That's problem 25.
Problem.
25 in the mission.
Oh, yes. Well, to show that the determinant is non-zero is basically show that the determinant. Oh, this was problem.
Yeah, that's
Okay.
what will happen when AD equals BC.
All right. Okay. Well, thank you. So, question: what happens if you? All right. Let me regroup a minute here. What are these? Like, what is a Mobius transformation? What are we looking at here? So it's a composition of a few different things, right? So first of all, if we look at f1 of z is equal to, say, cz, you know what that is. That's a what? A rotation and a dilation, right? So if c is a real number, it's just stretching out the vector. If it's got an imaginary part, then that rotates, right? It's a rotation and dilation. That's what this is. If we look at f2 of z equal to z plus say b, this is a translation, right? It's a translation. And so wait a minute. All right, so question: what does a multiplication by c do to a circle? If we took a circle, right? If we took a circle, actually it doesn't have to be at the origin, anywhere. Take a circle anywhere in the complex plane, right, z, and we look at this over here, what happens to it under the mapping f1, right? What does it look like over here? What's the image? So what's the typical point here? Something like what? Z naught plus r e to the I theta, yeah? And so we feed it to f1. What's f1 of z naught plus r e to the I theta? It's what? cz naught plus rc e to the I theta, yeah? Which is a new circle, right? With center at cz naught and a new radius. So it's like up here somewhere and it's bigger. I don't know, whatever. But it's still a circle, right? So rotation, dilation takes circles to circles. How about a translation? Does a translation take a circle to a circle? Indeed. Translation moves circles to circles of the same radius even, right? So if I had w equals to f2 of z, then the image of the circle would just be, new center b plus z naught. And same radius as originally. That's the image of the circle under translation. What else can you talk about? You can talk about inversion. f3 of z is 1 over z. So-called reciprocal map. What does that do to circles? Well, let's see here. We'd have I don't know. What happens if we plug in the formula for a circle, z plus e to the I theta? Or you could put e to the it if you want to parameterize it, yeah? What is 1 over z naught plus r e to the I theta? What's that look like? Not as easy to see, but in fact, it's still a circle. I mean, it's especially easy. If we put z naught equal to 0 for a second, it's obvious that it's a circle that's just oriented the opposite way around. Like it's just r e to the minus I theta. So in the case z naught equal to 0, it's easy to see it's circle. A short calculation, you can work it out. You'll be able to find an r tilde e to the I theta tilde for appropriate r tilde and theta tilde. You're going to be able to show actually. And in the center, I'm not sure where the center is. Right off the top of my head, actually. W naught, let's say. I mean, there is going to exist a new center, a new radius. It's somewhere over here. It's still a circle. And the thing is, this Mobius transformation can be shown to be a composite of these things. That's the theorem. Any Mobius transformation can be expressed as a composition of a finite sequence of translations, magnifications, rotations, and inversions. So this is actually two things. This is either a rotation or a magnification in the language of what I just wrote. So magnification would just be like c equals to r, a real number, right? Rotation would be c equals to e to the I, whatever, say theta. Complex multiplications are a combination of both of those things. So if you want to separate those, you could say, geometrically, a Mobius transformation is a composition of magnification, rotations, translations, and inversions. And it is, you can actually show that this formula is a composite of these three things. Okay? And there's more. You can prove that the Mobius transformation maps the extended complex plane one-to-one onto itself. So if we look at f of z equals to az plus b over cz plus d for z in C star, all right, then f of C star is C star. F is C star again. So it maps the extended complex plane onto itself. Furthermore, it maps the class of circles and lines to itself. In other words, it takes circles to circles or circles to lines. So this is easier to think about. If we come to the agreement that a line in the extended complex plane is a special kind of circle. It's a circle that goes through infinity, is the idea. With that understanding, you can just say that Mobius transformations always take circles to circles. It's just sometimes it takes a finite circle to a line, where the line is understood to be a circle through infinity. And furthermore, every Mobius transformation is conformal at every point except its pole. What's the pole of the Mobius transformation? Where's its pole? No, that's just not allowed. If AD is equal to BC, it is not a Mobius transformation. It's a constant transformation, which does not do any of these things. Like the constant transformation does not map the extended complex plane to the extended complex plane. It maps the extended complex plane to the constant. I will take a minus d over c. We have a winner, yes. So at every point except for that one, except for minus d over c, this function is conformal. And that's essentially proved by you in the homework problem, because you showed that the derivative, given that condition, and as long as you're not where z is equal to minus d over c, you have that the derivative is non-zero, hence it's conformal, meaning that it preserves the angle between points.
Oh, so it's defined that C star.
Yes. Now, there's much more to tell you about Mobius transformations. So, there's a theorem, and the theorem is as follows. If you give me 3 distinct points, all right, in the complex plane. Or we could say 1, 2, 3. I mean, whatever. Why do I have to start counting at 0? What's wrong with me? And I give you 3 points that you're mapping to, W1, W2, W3. All right? Then, and these are points in order, all right? Like, in the sense that these are an ordered set of points. I don't know. Then there exists a Mobius transformation that takes those 3 points to those 3 points in that same order.
Does it ought to be unique?
I think it's a unique Mobius transformation, yes.
No, I mean, the points have to be distinct from each other.
Yeah, distinct points. Yeah, yeah. Let's see here. Let me just look at a relatively simple. Let's just look at an example. I don't have time to develop this theorem. I mean, I can. Next time I'll go through the proof of this. It's basically going to be. No, I'm not going to say what it is right now. We'll go through the proof of this next time, and we'll introduce something called the cross ratio. There's like a simple calculational technique to write it down, but sometimes you can just kind of play with examples. We have time for that, so let's do that. If we have f of z is equal to, let's say, z, let's look at z plus 1 over z minus 1 and see what happens with it. All right. This is an example of a Mobius transformation. What does it do? So if I look at the z-plane, right, I've got minus 1. I can look at minus 1. I can look at 0, and I can look at 1. I can look at those 3 points, and I can see what this Mobius transformation does. All right. By the way, the Mobius transformation takes lines. It takes generalized circles to generalized circles. That's a generalized circle through infinity. That, in other words, that line either is going to map to a circle or a line in the W plane is what we ultimately learn as we sort out the theory of these things. So, and that's easy to figure out where it goes to. Like, you just plug it in, see what happens. What happens? So, like, what's f of minus 1? What happens with that? Minus 1 plus 1 over minus 2, also known as 0. So over here in the W plane, that maps to 0. Let me call this A, B, and C. So I'll call the image of, I'm going to call this big A. So little a maps to big A. What happens with 0? Looks like we got minus 1, right? I think the image of 0 under this map is minus 1. So where's that? Here, I suppose. You got to call me out if I did something wrong here. I think we're okay. What happens when we plug in 1? One plus 1 over 0. And so this extended complex plane that I haven't completely defined for you, but it has some, basically in the extended complex plane, we do all the things that you have been yelled at for doing in your calculus class. All right. So for example, division by 0, is it not defined? No, it's defined. It's just infinity. There you go. So this is infinity. So that's C. So it's way out here at infinity. That's where C is. So it looks to me, now here's the deal. This is kind of a funny map, actually. It looks to me like it's mapping half. So let's see here. if I go A, B, C, then what's on the left? If I start at A, then go to B, then go to C, what's on the left? If I think of these in this order, on the left it's up here, right? That's so, it's the interior of that boundary. Calculus 3 thinking. How about here if I go from A to B to C? What's on the left? Down. So this mapping F is actually a conformal map of the upper half plane to the lower half plane, right? Which actually maps the real axis to the real axis, but it also turns it over in that sense. I'm sorry, this example is not as interesting as I had hoped. I wanted to find one that actually took the plane and mapped it to a circle, because that's the really neat thing is once we talk about this for about a half hour more and get everything on the table, this gives us a tool to map half planes to any circle we want, or to map any circle to any circle we want. Yeah. What's that? Oh, well, they didn't do that yesterday. So anyway, thanks guys. I'm now behind.